And as always, I'll do my best to post this to my YouTube channel. Okay, so we kind of left off here. We finished up to section 9.4, so now we're on to section 9.5, which deals with the reduction of alkynes. And we're actually going to study 3 different reduction reactions in this chapter. The first one is one that you saw all the way back in chapter 8, right, which is just taking a pi bond and treating it with hydrogen gas and a catalyst, palladium, platinum, or nickel. Any one of those will work. And then I'll put here 2 equivalents of hydrogen plus palladium, platinum, or nickel. Any one of those metals will work. And instead of hydrogenating an alkene, so we only need 1 equivalent of H2 gas. When we hydrogenate an alkyne, we need, of course, 2 equivalents because we add a total of 4 hydrogen atoms, right? 1, 2, 3, 4. But you see that this reaction works in a very, very good yield. Now, if you're wondering, could I stop at the alkene? Is there a way to do that? Because I know it's syn addition. And so since it's syn addition, couldn't I stop at the cis alkene? And the answer is you can't using palladium, platinum, or nickel as a catalyst, but you can using a modified catalyst that we call a poisoned catalyst. So let's take a look at that. We call it a deactivated or a poisoned catalyst, and it can be used to stop the hydrogenation reaction once the cis alkene is isolated. So basically, you just use this special catalyst, which we call a poisoned catalyst, and I'll go over that in a second, and you end up with a cis alkene, and it doesn't reduce any further. So what is this magical poisoned catalyst? Well, the main catalyst that we use is what's called Lindlar's catalyst, and it is a concoction that you see down here at the bottom of your screen. So it's made from quinoline, and it's got lead acetate sometimes, or lead 4 oxide in it. Anyhow, you can see that it's got barium sulfate. Anyhow, I'm never going to ask you about the structure of Lindlar's catalyst. Usually my students will just write Lindlar's catalyst, and that is totally acceptable for saying I'm going to hydrogenate directly to the cis alkene, and I'm going to stop there. There is another version of a poison catalyst that works, and that's called the P2 catalyst, which is a nickel boron complex. Now, I don't think the book uses this a whole lot, but I have seen this, the P2 complex, mentioned in MCAT materials and ACS materials. I think ACS, but I'm pretty sure I've seen it in the MCAT materials. So you do want to be aware of the P2 catalyst. And maybe it does make an appearance somewhere in our textbook, but that's a poison catalyst, but it's not as commonly used as Lindlar's catalyst is. So if you're wondering, how does this catalyst function? Well, it's nothing more than this. Is if you look at the reaction coordinate diagram, is that all it does is it lowers the activation energy of the first step, right? The activation energy of the first addition of the first molecule of hydrogen is really high. And so what it does is it lowers that activation energy to something much, much lower. So we'd call this maybe EA prime or something, but it doesn't affect the second step. So once you get to the cis alkene, it's done. So you get the cis alkene and the reaction is finished, done, kaput. Okay. So again, to rehash, the way you would write the arrow is you would put arrow, you'd put hydrogen gas, and then you would write Lindlar's catalyst. You could just abbreviate it like that. And I'm totally fine with that. So then you might be wondering, well, if we can make a cis alkene, is there a way to make a trans alkene? And the answer is, yeah, there is. There is a way to make a trans alkene, and it's using what we call dissolving metal reduction. So we put sodium metal, which is a solid, of course, we put it in liquid ammonia. So it's sodium in liquid ammonia. And of course, sodium has 1 valence electron, right? It ends off with 3s1, so it's got 1 valence electron. And this is actually a radical mechanism, and we don't look at radical mechanisms until chapter 10. But I digress. The idea is this, is that you end up with anti-addition. So you end up forming a trans alkene in the end. You end up with the trans alkene. And so now you have a way to make a cis alkene, and you also have a way to make a trans alkene. Now, I'm not going to quiz you on the mechanism of this reaction of the dissolving metal reduction. However, there is one thing that I want you to understand, is that the intermediate that it passes through is called a radical anion. Okay, that's the intermediate that it passes through to get to the trans product. And the radical anion explains why this reaction is stereoselective for anti-addition, versus a mixture of cis and trans or syn and anti addition. So if we look at the radical anions, so these are radical anions right here, we see that we have a radical, right? A radical is an unpaired electron, and that we also have an anion. That both of those possess electrons. One possesses a pair of electrons, the other one possesses an unpaired electron. But are those going to be attracted to each other or repelled by each other? Well, they're going to repel each other, and so they're going to end up on opposite sides of the double bond. And that explains why after we get another electron donated from sodium, we end up with two anions and we end up protonating both of those. Anyhow, I'm not going to go into the mechanism, but the radical anion that's shown here, okay, this one is lower in energy, and that explains why we end up getting the transalkene. So this is the radical anion, and that gives us the transalkene. Okay, the one that's higher in energy would lead to the cis, and we don't get the cis because it's higher in energy. Now again, you can look over mechanism 9.1, which covers this mechanism from soup to nuts, but you don't have to know the mechanism at all. Okay, you don't have to know it for this chapter quiz. Don't worry about it one bit. We're going to look at radicals more when we get to chapter 10. So what's a summary of section 9.5? It's nothing more than this. We know the reagents to take an alkyne and convert it all the way to an alkane. That's just our good old chapter 8 conditions. Hydrogen and a metal catalyst, palladium, platinum, or nickel. But now we also know how to make a cis alkene via syn addition, right? So syn addition leads to the cis. And we know that we can use dissolving metal reduction to do anti-addition, which passes through a radical anion intermediate, and that gives us the transalkene. Now, of course, you can take the cis or trans and hydrogenate them the same way you did in chapter 8, but this shows you that you have a lot of power now with an alkyne to reduce it to a trans or to a cis or all the way to an alkane. So that would be the summary of section 9.5. So let's try a practice problem here, and this isn't meant to be a mind boggler or anything. It's just more to get us to practice the reaction conditions. So for the first one, if we want to take an alkyne and convert it to a cis alkene, we know that our conditions are going to be hydrogen gas, right? And we're going to use Lindlar's catalyst to do that. If we want to do the if we want to form the transalkene, I'm getting ahead of myself here, we're going to use the dissolving metal reduction. So we use sodium in liquid ammonia. The next one is the same thing. We're doing the reduction of an alkyne to a transalkene. So we use sodium and liquid ammonia. And the last one, we're hydrogenating it completely. So we would use hydrogen gas and palladium, platinum, or nickel to do that. So that's just kind of a rehash of this. Before we move on to section 9.6, I'll just show you one mnemonic that my students taught me a few years ago, is that when you're forming the transalkene using dissolving metal reduction, the way that they taught me to remember it is the sodium starts with the letter N, right? Or the atomic symbol is natrium, right? But anyhow, so you get the letter N, and it kind of looks like a transalkene. So maybe that's helpful for you. Maybe it's not. I don't know. But there you go. So sodium starts with the letter N, and it kind of looks like a transalkene like that. Well, let's move on to hydrohalogenation. And hydrohalogenation follows the same rules that hydrohalogenation did of an alkene. If you're like, what's hydrohalogenation again? Hydrohalogenation of an alkene was this. If we had something like this and we treated it with HCl, it was the whole idea that the rich got richer, right? You ended up with this. You ended up with Markovnikov addition. And so the same rules apply with an alkyne, right? The same rules apply that the rich get richer. If we look at this alkyne here, you see that the terminal carbon is richer in hydrogens, and so that's the one that takes the second hydrogen, and we end up with our halogen here. And so if that's using one equivalent of HX, whether it's HCl or HBr, if you use excess, then you end up with a geminal dihalide. So I actually misspoke earlier, and I said, oh, we're going to make vicinal dihalides. I shouldn't have said that. We're not making vicinal, we're making geminal dihalides. One thing that I noticed in my slides here is that I kind of mixed two concepts on this slide and the neighboring slide. So the first statement here, so I'll just highlight it in yellow. This statement applies to this reaction here, okay? You do not need to know the mechanism. So I'll just put it here. Do not need to know the mechanism. And the reason why is it's actually kind of complex. It's what we call a termolecular reaction. It's a third order reaction. So I'm not going to go into that since you don't need to go over it, or so I'm not going to test you on it. But you do have to know that you can do an Antimarkovnikov addition of HBr only. Doesn't work with HCl, doesn't work with HBI, but if you use HBr and organic peroxides, you will get an Antimarkovnikov addition of HBr across a triple bond. So of course you use HBr and organic peroxides. Again, this mechanism will be covered in chapter 10, so you do not have to know it for this quiz. Now, when you do the Antimarkovnikov addition, you end up with a mixture of the E and the Z isomers. All right, now whichever one is less sterically hindered is probably the major product, but again, don't worry about that all that much. All right, so now we know how to make a dihalide by treating an alkyne with excess HX. I told you this is a termolecular mechanism. I'm never going to ask you about it, but it does follow Markovnikov addition. So we'll put here Markovnikov addition, right? The rich get richer. And then we can take that dihalide and we can do a double elimination, followed by deprotonation, followed by addition of water to make a terminal alkyne. And so we can go back and forth. These are kind of like complementary reactions, so to speak. So with all that in mind, let's see if we can try a practice problem here. It just says predict the major product expected for each of the following reactions. So we're taking this geminal dihalide and we're treating it with excess sodium amide followed by treatment with water. Well, what's that going to give us? That's going to give us the alkyne. So we're going to draw the alkyne, which would look something like this. You could call that phenylacetylene, would be the common name. And then in the second step, we're going to treat that with HBr and peroxide. So that's going to do an anti-Markovnikov addition of HBr. So we're going to end up with two compounds. We're going to end up with the trans compound, and we're also going to end up with the cis compound. We'll end up with a mixture of both of those. We get, again, the trans and the cis compound. Now for the second one, the first step is identical, so I'm just going to copy and paste this guy over here. So copy and paste. I think it's faster to just draw it, huh? So the first two steps are going to be the double elimination followed by protonation. And then the second step is to treat it with excess HBr. So that's going to halogenate it twice. So instead of having the geminal dichloro, we're going to have the geminal dibromo. I don't know what the purpose of this reaction is, but I guess just to practice the rules really more than anything. So I'm regurgitating the starting material. So we end up with a geminal dibromo in this case, right? Because this one is going to give us Markovnikov addition, like that.